For ages, the mysterious splendor of the universe has enticed us from its remote heights. At last, its mysterious temptations are within reach, and man's destiny can be fulfilled.
I don't know if it's written in our genes, but anytime you see something at a distance and it piques your curiosity, the first thing you want to do is get a closer look. So while telescopes get you pretty far in this regard, those things that are sort of close enough to be within the reach of our space program, why not take the trip?
T-minus 10, 9, main engine start, 5, 4, and liftoff of Space Shuttle Atlantis to assemble.
Prying free from our home planet's grip ranks among the greatest of human achievements. But no one, since 1972, has ventured beyond the Earth's orbit.
Our space program has been stuck for 30 years. We simply just go around the planet Earth. It's just like Columbus exploring the New World for the first time and then spending the rest of his life simply puttering around the Spanish coastline. What's the problem? There's a dirty little 4-letter word, and that is cost. It costs about $10,000 to put a pound of anything into orbit. Imagine John Glenn made out of solid gold. That's what it costs to put John Glenn or you into orbit. It would cost about $20 million for you to take a weekend trip up to the space station. It would cost about $500 million for you to go to the moon. And for you to go to Mars would probably cost tens of billions of dollars.
One way to reduce the cost of reaching space would be to find a more efficient way to overcome Earth's gravity.
Remember the story of Jack and the Beanstalk? Jack was the little boy who climbed the beanstalk into heaven. Well, imagine a space elevator such that you hit the up button and the elevator takes you into the heavens just like Jack and the Beanstalk.
Instead of building from the ground up, the space elevator would be built from the top down. A satellite in geosynchronous orbit would drop a 60,000-mile cable back to Earth, where it would be anchored to the surface.
Now we are within striking distance of being able to create fibers that can withstand the tension of traveling at enormous velocities in outer space as the space elevator rotates with the planet Earth. So it never falls because it rotates at the same rate as the planet Earth.
The elevator's compartment would simply roll up the cable, shuttling travelers and supplies into orbit, where it would wait for a spacecraft. This system would entirely replace a conventional rocket launch.
And that might reduce the cost of space travel by a factor of 1,000. Think about that. Then you begin to realize that perhaps a trip to outer space may be no worse than an airplane ticket.
But beyond the limits of Earth's comforting embrace, exotic menaces await every space traveler.
Flying in outer space is not like taking a nice ride in the country in a car. It's like going through a shooting gallery.
To an unsuspecting voyager, it might seem the universe is taking aim with a firearm.
There are particles in space, even dust-sized particles, pebble-sized particles, that are traveling tens of thousands of miles an hour and sometimes even faster.
More than 500,000 of these projectiles, measuring over 1 inch in diameter, are zipping around our planet right now. They include pieces of glass broken off of solar cells, paint chips from spacecraft, and debris from rocket booster engines. And in deeper space, there's more danger from pebble-sized meteors called micrometeoroids.
A small piece of dust can crack glass, it can penetrate metal, it can pulverize plastic. And that does happen in space all the time.
But perhaps an even more deadly danger, not at all solid, lies in wait: radiation. The devastating effects of this invisible energy have been witnessed on Earth in the aftermath of the atomic bombs of World War II and the nuclear fallout of Chernobyl. Distressingly, our own life-giving sun spews out streams of poisonous radiation.
So realize that we've been protected in this cradle. We've been protected by the atmosphere of the Earth. Magnetic field of the Earth gobbles up most of the flares from the sun to create the aurora borealis. In outer space, you get the aurora borealis coming right at you. There's no ozone layer, there's no magnetic field to protect you. It's just you and the harshness of outer space.
At our home planet's distance from the sun, roughly 90 million miles away, several hundred million solar particles pass through each square inch of space every second around our Earth.
There's high energy particles streaming from the sun all the time. But every now and then there's an extra dose of these particles. The sun burps up high energy radiation. That's bad too. That level of radiation is never good for one's DNA.
Sunspots flare up these extra doses of energy like a battery of cannons bombarding the cosmos.
There's no way to know that they're going to be here before they arrive.
Unfortunately, there's still a risk of radiation even as we get farther from the sun. That's because another invading energy lurks. Known as galactic cosmic rays, they hail from the distant alien worlds of exploding stars and black holes.
Galactic cosmic rays are particles that are traveling at speeds very close to the speed of light. Even a single particle of iron slamming into your body can have the effect of a Major League Baseball at 100 miles an hour. They can be devastating.
Although heavy iron particles are rare, outside of the protection of a spacecraft, such as when an astronaut performs a spacewalk, thousands of galactic cosmic rays do penetrate the body every second. Every 24 hours, the galactic cosmic rays and solar particles attack a space traveler with as much radiation as a surface dweller on Earth receives in 6 months. The human body won't immediately feel the impacting radiation, but in sufficient quantities, it can be noticed. Even with eyes closed, the particles spark flashes when they strike a space traveler's retina.
The flashes are not blinding, and you have to ask yourself, did I see something? And then you say, oh, yes, I did. And its appearance is a little different from time to time.
However, the human body does feel the shock of this bizarre weightless existence.
I think that the most dangerous thing going into space is the loss of gravity. Weightlessness causes almost every system in your body to start changing. And it doesn't stop changing until you get back onto a world where you're pulled down again by its gravity.
One of the first casualties of zero gravity is a space traveler's sense of direction.
What's up and what's down? Very good question. And first of all, it's whatever you want it to be. If you want this to be up, that's fine. But if you want this to be up, that's just as good.
Most travelers will suffer from motion sickness for the first few hours, or most likely, days.
It's just one of those things that you ought to resign yourself to facing, that everyone is very likely to feel a little bit disturbed in terms of orientation.
Here on Earth, scuba divers floating underwater experience the nearest sensation of prolonged periods without gravity. It is for this very reason that aspiring NASA astronauts train to live and work in a gravity-free environment by subjecting themselves for up to 6 hours at a time in a large water tank.
Now, scuba equipment, you still experience the forces of gravity, but it doesn't feel like it because your whole body is uniformly buoyed by the water that holds you up.
And except for the visual cue of air bubbles floating to the surface, swimming underwater can mimic the sensation of disorientation. But as time passes in the weightlessness of space, the human body senses it no longer needs to resist the force of gravity and begins shedding muscle and bone mass.
When you're in space, your body thinks you might as well be lying in bed. And so if you're not careful, your body will atrophy.
To counter this, each day in space, an astronaut needs to exercise. The legs are especially vulnerable because they are seldom used. In this world, the arms and hands do most of the work to move the body around.
What would be the toughest thing to get used to might very well be just how you live in space, where you can't walk across the room. You have to float everywhere you're going.
The lack of gravity also slows down the digestive tract, which can cause problems at mealtime.
Your digestive system stops. You can't eat, you can't drink until you can start digesting again. And that can take anywhere from hours to days.
Worse still, zero gravity and radiation can combine in an especially sinister way.
In space, the immune system is not as effective as it normally is. And many of the bacteria and viruses that we normally can withstand become more virulent.
Additionally, bacteria can grow up to 50 times faster, and any virus brought on board could mutate into a never-before-seen predator, thanks to the ever-present radiation. All these difficulties prey on space travelers in just the first few hours or days. And what about journeys that need more time? It only gets tougher. The universe is an unforgiving place. It's open to only the boldest adventurers, those who have the mettle to trek deep into an environment swimming with toxic hazards, and unafraid to stray far from the safe and familiar.
We take it for granted that clothing is flexible and machines work in room temperature because implicitly or explicitly, they're designed for that. You go into the depths of space. If you're facing the sun, it could be hundreds of degrees Fahrenheit. If you're facing away from the sun, it could be hundreds of degrees below zero.
Down here on Earth, you take so much for granted. You know, we're out here, sunshine, the fresh air all around you. Up there, you're in a closed ecosystem. You have to supply all the human needs that the Earth just, automatically does for us. You have to hope that the integrity of the hull stays together so you don't have rapid decompression, quick suffocation.
The same reality exists for a submarine gliding deep through the ocean. It provides a life-preserving barrier to protect its inhabitants from a surrounding alien world.
If there's damage to the spaceship, air leaks out, you die. Damage to the submarine, water gets in, you die. So the isolation, both physically and personally, between the two seem quite parallel.
The potential for a catastrophic mishap lurks.
When you're out in the middle of the ocean, you have only yourself and your colleagues to rely on. And the same thing applies in space.
Things have to hold up. You can't come back, you can't run to the hardware store, you can't fix the thing with some part that you didn't bring along, and you're stuck with human ingenuity, the tools you brought with you. And out there in space, you truly are just removed from mankind. It is isolation like I've never felt before.
Liftoff. We have liftoff.
Often Our efforts to explore space have been analogized to the great explorers of the 15th and 16th century. The first to sort of cross the oceans, going to unknown territory, having to bring all their supplies with them, not knowing if they'll ever return. And I think there's a lot to say about that analogy, but there's a point where it breaks down badly. When Cortez landed in South America, when Columbus hit the Caribbean, there was still air there for him to breathe, all right? There were fruit on the trees. Suppose the Apollo 11 astronauts, Neil Armstrong and Buzz Aldrin, landed on the moon and, like, the engine broke.
Okay, Houston, we've had a problem here.
What do? Nothing. You just die. There's not sort of an engine tree that they can pluck parts from to repair their ship. So the hazards are vastly greater to human health in space exploration than traveling anywhere on Earth's surface.
There won't be any service stations in case you break down, run out of gas, or need something to drink.
One of the challenges of space exploration is either carrying along with you all the supplies you need, water, food, oxygen, or finding some way to manufacture that en route or at your destination. We're not there yet. We don't know how to do that yet. And so one hazard is if something goes wrong and you run out of food and water and shelter, that's bad. You'll die.
Every sip, every drop of water is precious. On a space voyage, there will be no such thing as a shower. The only option will likely be a wet cloth. This is quite a change from the 130 gallons of water each American consumes in just one day. The cuisine on board would take some getting used to as well.
For a few days, you can take fresh fruits and fresh vegetables, carrots and apples and things like that. For the longer missions, though, you have to have storable foods that can, stay for long periods of time without spoiling and going bad.
And yet, astronauts agree that enduring the myriad of risks is a small price to pay for the chance to witness the wonder of the cosmos in person.
1500's 2.3.
I know how they felt because they report things like, well, you could hold up your finger and you could block out the Earth with your thumb. And it kind of gave them an entire new perspective of how amazing this little blue marble the Earth is and how precious it is in this vast solar system.
That experience changed me forever, and I think it would change anyone that could possibly have that experience in the future.
However, the length of future voyages might limit the range of experiences available to space travelers. Distances in our vast universe can defy comprehension. If our sun were the size of a basketball, our Earth would be the size of a pea. If they were placed in Central Park, the nearest star would be another basketball almost 5,000 miles away in Hawaii.
One of the prerequisites you might have for a space mission is that you're alive when you arrive at your destination. So you'd want your space missions to be small compared with the life expectancy of a human being. And right now, that pretty much limits us to the planets and possibly comets and asteroids, if we include those as places we might visit.
The brutal, scathing landscapes of the solar system's inner planets, Mercury and Venus, do not make for tempting vacation destinations. Temperatures on Venus can exceed 900 degrees Fahrenheit, and the crushing air pressure is equivalent to being submerged in 3,000 feet of water. That leaves all points further out from the sun for potential exploration. But even trips to our closest attractions will still take several months or even years. About 139 million miles separate the orbits of Earth and Mars. But since each body circles the sun at different speeds, the distances with respect to each other change continuously.
The problem with going to Mars is that Mars and the Earth only line up about once every 2 years.
With current chemically propelled rocket technology, a flight leaving from Earth for the Red Planet in 2018, when the two bodies are on the same side of the Sun, could take 104 days, less than 4 months. After a 40-day stay, the return trip would require a little more than 6 months. That's an entire year to make one round trip. But a voyage departing in 2031, when the Earth and Mars are on the opposite sides of the Sun, would demand about 20 months, nearly 2 years of travel time. That's 1 to 2 years away from any lifeline. Comets, those oversized dirty snowballs, swoop close enough to Earth to accommodate a round trip lasting as short as a few months.
Find some comet that's on its way into the sun and ride it. And watch the coma grow and the tail form. And watch the sun first slowly, but then rapidly get larger and larger and larger. You swing around the backside and come out. It's got to be the most fun tour of the solar system you can come up with. It'd be dangerous because particles of the comet would fly up and hit you in the face and things. So apart from all that which would kill you, it would be a fun trip.
Just beyond the orbit of Mars, asteroids fly within range of a few years round trip from Earth. Future travel agencies might arrange cosmic versions of extreme vacations by exploiting the unique environments of these miniature planets.
They put you on a sled and slingshot you into space in such a way that the weak gravity of the asteroid will hold you in orbit but won't pull you back down again. Would be a great ride.
3 times farther away than Mars, the orbit of Jupiter, with its crowded moon system, offers dozens of diverse visions. It may prove tempting for future travelers, but a round trip could take 5 years. Saturn is nearly twice as far as Jupiter, and the thought of decade-long trips might be too much to bear. But there are technologies that can slice the time it takes to visit Mars to just a few days. For mankind ever to venture into the depths of the cosmos, endeavor to bathe in the light of an exotic star, or even just a voyage to the suburbs of our own solar system, we'll need to find a way to travel much, much faster. What's the fastest we could travel? Nothing yet observed by science moves faster than the speed of light, 186,000 miles per second.
The speed of light is the ultimate velocity in the universe. It's Einstein's cop on the block. The speed of light is so fast that you could go around the Earth 7 times in just 1 second. For you to jump to the moon at the speed of light, you could reach the moon in about 1 second.
Compare that to the 3 days it takes to get there with current technology. The problem is that we can't travel at the speed of light, or really anything even approaching it.
Take the fastest thing we have ever sent anywhere and ask, how long will that take to reach the nearest stars? That would take 50,000 years.
And that is using current chemical propulsion, which maxes out at about 40,000 miles per hour. The same power source we use to lift our rockets off of the planet. But getting us to Mars faster than a few months' time would require a different kind of propulsion. There are a few ideas for how to propel us to velocities closer to the speed of light, which would be fast enough to get us anywhere in the solar system in under a day, or even to the nearest stars in less than a decade. One such theory echoes an ancient earthly propulsion device, wind pushing a sail.
It was Kepler, that great astronomer, who first wrote down in his notes the possibility of using sails to sail in outer space.
Light streaming from the sun mimics gusts of wind in outer space. This solar wind is what creates a comet's tail as it nears the sun. However, sunlight scatters in all directions, and as the distance from the sun doubles, its power reduces by a factor of 4. With a little help from the moon, there is a manner in which light could be focused in one direction.
If we have a battery of laser cannons on the moon, firing in synchronization at a solar sail, we may be able to propel it to about perhaps half the speed of light. Now, lasers do diffuse with space. For example, if I have a laser on the Earth and I shine it to the moon, it does not create a spot on the moon. The spot is about 5 miles across on the moon. These sails, however, would be huge. Now we're talking about astronauts, perhaps spending months in outer space, designing a sail hundreds, maybe even thousands of miles across, sufficiently light and durable in order to capture light from a battery of laser beams on the moon.
But solar sailing limits space vessels to destinations within our solar system. One alternative gets around this problem by tapping into hydrogen, the most abundant element in the universe, as a propulsion source.
My favorite design to take us to the stars is the ramjet fusion engine. The ramjet engine has a gigantic scoop in the forward direction that gobbles up hydrogen gas as it moves in deep space. It collects the hydrogen gas and then fuses it, just like the sun, and shoots out a huge stream of ions out the other end. And on paper, it looks fantastic. On paper, it looks as if a ramjet fusion engine could go on forever, simply using up the hydrogen that is found naturally in outer space.
Unfortunately, scientists have not yet been able to achieve a hydrogen fusion reaction capable of propulsion in tests. But another potential fuel source, one that seems to come right out of science fiction, has already been created in laboratories. It's called antimatter, and it's the opposite of all that we know.
For example, think of the world on the other side of the looking glass. Just like in Lewis Carroll's Alice in Wonderland, we physicists have wondered, is there another universe on the other end of the looking glass? A parity-reversed universe where left becomes right, right becomes left. In an anti-universe, charges are reversed. So positive charges become negative, negative charges become positive, and when they meet, they create a burst of energy. So if this universe on the other side of the looking glass were made out of antimatter, and I were to touch this other universe, I would destroy most of the New York City metropolitan area in a burst of energy. So the conversion of antimatter and matter to energy is 100% efficient. It is the ultimate engine. But there is a catch. There's always a catch. Even though we can create anti-atoms in the laboratory, the cost is stupendous. It would bankrupt the United States of America to create a teaspoon of antimatter. However, it would only take a few grams of antimatter to take us to Mars, and perhaps several teaspoons of antimatter to take us to the nearby stars.
But for us to ever visit a distant star or another galaxy, we need something stranger than even Alice could ever dream of, peering through her looking glass. Scientists continue the quest for a propulsion method to carry us ever deeper into space. But even achieving light speed won't allow us to get very far.
Light's fast, but the universe is huge. So even if we could ride on a beam of light, if we wanted to cross the galaxy, the way they do in all the science fiction programs, it would take 100,000 years to do it.
And even at light speed, traveling to the nearest galaxy would take several million years. And if light speed is the ultimate speed limit of the universe, it seems we're doomed to confinement in our galactic neighborhood.
What we're desperate for is some new understanding of the fabric of space-time that will allow us to somehow warp it, distort it, so that you can take shortcuts. And of course, that's what they do in Star Trek when they turn on their warp drives. They want to get from one side of the galaxy to the other. All they do is invoke the warp drive that warps the fabric of space, and then they take a little shortcut right there. They cheat, basically.
Everybody knows Einstein's famous dictum, you cannot go faster than the speed of light. However, there's a footnote to it. You see, Einstein left open the possibility that you can fold the fabric of space and time itself so that you effectively take a shortcut through the universe. Think of a carpet. If you want to go across the carpet, that's the old-fashioned way. You can also get a lasso a table on the other side of the carpet, and then drag the table toward you so that you collapse the space in front of you. In a nutshell, Einstein says the bigger the mass, the bigger the bending of space and time. If you can concentrate enormous amounts of energy at a single point, comparable to that of a black hole or a huge gigantic star, you are literally warping the fabric of space and time. You simply hop across to the nearby stars. So in other words, you did not really go to the stars. The stars came to you because you are compressing the space in front of you.
The massive amount of energy or mass needed to create such a warped curvature of space seems beyond comprehension and perhaps beyond human capability. There may be an alternative. Physicist John Brandenburg is developing a theory in which a starship of the future could achieve faster-than-light travel, not by manipulating a vast area of the universe, but rather by manipulating only the area around the starship. The trick is to have a starship imitate a curious particle that so far only exists in theory. It's called a tachyon.
It's a particle with a different twist. Light itself always moves at the same speed. Tachyons, on the other hand, can go infinitely fast. They just can't go slower than the speed of light. They look at the speed of light as a lower speed limit that they cannot violate.
If they do exist, tachyons can outrun the speed of light because they have what physicists recognize as imaginary mass. An imaginary value can be visualized in the spin of a struck tennis ball. Its spin can cause it to bend and move in a manner that an observer might not expect to see from its initial point of contact. In the same way, a tachyon is unseen by the universe and can break its speed limits. Brandenburg proposes altering the space-time surrounding a starship with a powerful electromagnetic field so that the ship moves through space like a tachyon. It would operate like a stealth aircraft, invisible to radar, unseen by radar operators.
So if one can achieve this control of the space-time around this ship, one can essentially make it an imaginary object. In a technical way, that means it's moving faster than light. You're basically disconnecting yourself from the rest of the cosmos.
It could grant the traveler the ability to go anywhere in the universe in the blink of an eye, as if a multitude of doorways suddenly appeared.
A doorway you step into and then you step out somewhere down the hall so fast that it didn't seem like you had time to move anyplace. That's an imaginary connection in space-time. And you've changed yourself, not space-time.
No one may know how fast or even where such a space vessel could travel.
Which door to go into, which door to come out of. That's the trick.
But voyaging through the Hall of the Universe isn't possible without first overcoming one of its fundamental forces, the one that shackles us to our home planet.
Getting away from the Earth's gravitational field. That's the first thing that we have to do.
10, 9, 8, 7, 6.
For an object to
5,
break away from
4,
Earth's gravitational
3,
pull,
2, 1. We have ignition and liftoff of NASA's New
it must
Horizons
achieve a velocity of 17,500 miles per hour. That's fast enough to streak from New York to Los Angeles in about 8 minutes.
There's no other way to do it, at least that we have now, other than brute force.
While a theoretical space elevator can climb away from Earth's gravitational pull, a rocket must outrun it with the brute force provided by the explosive chemical reaction of burning fuel.
Chemical power is what drives today's rocket engine. Every time you burn something, that's chemical power. Every time a rocket engine ignites, that's chemical power. Every time you start your engine in your car, you're using the chemical energy stored in the gasoline.
The fuel alone can burden a spacebound craft with up to 90% of its total weight.
If you're carrying all the fuel you'll ever need, then most of the effort of the first ignited fuel is to lift the unburnt fuel into orbit. It'd be like trying to drive from New York City to Los Angeles on one tank of gas. Well, you would need a tanker truck behind you. And most of the energy to accelerate the tanker truck is going in to just move the fuel that's in the tanker truck.
The space shuttle, its rockets, and the fuel they're carrying weigh a staggering 4 million pounds. And nothing short of a bone-rattling eruption could push it up and away from Earth.
Well, Brent, looks like your long wait is over. We wish you all the best luck in the world. Godspeed, and we'll see you back here in about 2 weeks.
A journey into space today means that space travelers must ride a controlled detonation into the sky.
Whatever the vehicle weighs, we have to generate about 1.5 to 2 times that thrust in order to get it off the surface of the Earth.
To get the space shuttle up to speed demands 7 million pounds of thrust. To put that into perspective,
if you can imagine me holding a 1-pound ball in my hand, if I'm holding it here and I'm holding it steady, I am exerting a pound of thrust on that ball. So if I lower it down, I'm clearly not exerting a 1 pound. If I pick it up, I'm exerting more than a pound. So you have to have a little more thrust than you do the weight, obviously, or you won't go anywhere.
How a rocket moves can be illustrated with a blown-up balloon.
This works almost like an engine nozzle. Now I can hold it in place, and you can control it. You can let it go. And what we do is we try to eject as much mass through that throat as we can. And as it expands out, the back end, that expansion or that pressure pushing that way pushes the vehicle this way.
When today's astronauts climb aboard for their journeys on the space shuttle, they're hitching to giant containers housing that necessary mass. Millions of pounds of highly combustible hydrogen and oxygen wait to be ejected. It only takes a spark.
The main engine starts 6 seconds before takeoff. The whole shuttle shakes. It feels like it wants to just rip itself out of the launch pad.
Off of Space Shuttle Endeavour, expanding the International
It shudders,
Space Station.
and you think, oh my gosh, that's an awful lot of force, about 1.5 million pounds of thrust. It's kind of surreal. It's like, this can't really be happening. It's something you've been wanting to do for years and years, and it's really happening. It's like riding a man-made earthquake. You've spent several million pounds worth of fuel to get to the first 2 minutes of flight, and then the solid rocket boosters come off. And that's like a train wreck when those things come off. It almost feels like you're just accelerating faster and faster and faster as you burn all the fuel out of the big main tank. So for the next 6 minutes, you're accelerating up to a point where you're finally feeling about 3 Gs, 3 times the force of gravity of acceleration. And so now it almost feels like there's a big gorilla sitting on your chest.
A drag racer who accelerates from 0 to 100 miles per hour in 2 seconds will feel G-forces similar to those experienced by astronauts.
As the vehicle keeps accelerating and you're watching the speed tick by in thousands of feet per second until you get to 25 times the speed of sound. Then there's a cutoff, and then everything's floating. And now you're in space. So space isn't very far away. It only takes about 8 minutes and 30 seconds to get there.
The next model for venturing into the great beyond and reaching new worlds will begin first with a visit to an old friend. Although not quite yet a space elevator, NASA's mission to return to the moon builds on the idea of Earth orbit as a base for farther voyages. NASA's Constellation program, a successor to the legendary Apollo program, aims to plant boots on the moon by 2020. 2 separate rockets form the foundation of the plan. The unmanned Ares 5 rocket, towering taller than a football field standing on its end, will carry the lunar lander, supplies, and an Earth departure rocket into orbit, where it will wait for the astronauts. The Ares 1 rocket will deliver the crew to orbit aboard a capsule. It will then rendezvous with the Earth departure rocket and blast to the moon.
We can take more supplies, more commodities to the moon. That's what this tandem system provides for us. Instead of Apollo, which only allowed us to go for 1 or 2 days at a time and then come back.
Will we ever find a way to surpass the bold achievements of the Apollo program? Will we ever cross the vast expanse of the cosmos as quickly and effortlessly as we travel to another city or another continent? We must if we are to survive as a people.